Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you understand how to say derive velocity functions for a given object when you're trying to analyze the motion of a particle. So first of all, we're going to talk about this car here, this animal right here. And the first thing you do when you're studying the motion of an object is you define a set of coordinates. So I've done that right here. Now, where you put this really doesn't matter. You can put it anywhere in the picture you want. You tend to, you generally want to put it somewhere that makes some sort of sense. I'm going to go ahead and just leave it right here behind the car. And now, because of my choice, the car is starting with some x initial, which would be, let's say we measure it to this dot on the car. X initial would be now this distance at some positive value, right? The y-coordinate of the car is 0 because of where I put the coordinate system. And this is a one-dimensional problem. We're only going to worry about the x-coordinate of the car. So it's starting out at some positive value. Now, what x is doing will depend on what the driver is doing here, okay? So if the car is in forward, x will increase. And I'm going to talk about 3 different possible cases here. All right, case 1. The car is moving, but the acceleration is 0. So it's moving at some velocity to the right. Now, what that velocity is doesn't really matter. I'm just going to call it v initial, v sub o. So when we draw our velocity graph, we ask ourselves, all right, at t equals 0, what's the velocity of the car? That's what this is, the v sub o, which stands for v initial. If the car is moving to the right and we've got right positive, that is a positive number in our coordinate system. So we come over here and we sketch our graph. Now, the reason why that's horizontal is because if the acceleration is 0, then 1 second later, the velocity is still whatever v sub o is, which is this distance on this graph. A second after that, we'll call it 2 seconds, still v sub o. A second after that, and so forth. Now, the way you derive equations, if you will, is rather than stopping it at 1 second or 2 seconds or 3 seconds, we'll just call it t. Now, the point of this video was how to find the velocity functions. I'm going to make a separate video on how to find the position functions, but in this example here, the velocity is not changing. So the v of t is whatever v sub o is. And that's it. It's a positive number. In this case, the velocity is to the right and we have right positive. If the car were moving to the left, like the driver had it in reverse, but again, still 0 acceleration, this would be some negative number. This would be down here, something like that. So there's our velocity function, and in this example, it's just a constant function, whatever this numerical value is. All right, let's look at a second case here. The velocity and acceleration are in the same direction. So imagine this car is moving already to the right, and the driver gives it gas. So in that case, the velocity is to the right, and it's going to increase, meaning that the acceleration also to the right. At t equals 0, the velocity is some positive value. So on this graph, again, this is what I would typically call v initial. You might see it in another book written v sub I here. It doesn't really matter. V sub o is a very common variable for that. So if the car were moving at 3 meters per second, that would be your 3 meters per second. Now, if the acceleration is in the same direction as the velocity, that means that the car's velocity is going to increase. So a second later, we're going to have a bigger number, meaning a little higher on the graph. Second later, bigger number, a little higher on the graph. Now what we're going to do here, again, kind of like I mentioned before, we're just going to stop this at some arbitrary time. Rather than calling it 3 seconds, 4 seconds, 5 seconds, we're just going to call it t. Now, the reason I drew this straight, in a physical problem, you generally ask yourself, is the acceleration constant Or is it reasonable to assume so? In most of the problems that you deal with in a standard college physics class, most of the time you'll be dealing with problems where it is reasonable to assume constant acceleration, which means your velocity graphs are linear because, remember, accelerations equal to change in velocity over change in time. So acceleration is slope of a velocity versus time graph. So, whoops. Here is our velocity graph. It's going to look something like this. All right, next, all right, finding this function. There's a couple ways here to do this. I'm going to go through this approach. All right, that is a linear function. All linear functions can be written in this mathematical format, y equals mx plus b. Probably saw this in algebra class quite a bit. Now, this isn't a graph of y against x. I'm only writing this down because if you're right out of college algebra, you probably saw this thing about 125,000 times maybe. Our graph here on the vertical axis is v, right? The slope, the m, right? Acceleration, remember, is the slope of your velocity graph, right? Instead of x, our independent variable is t. And then the b is the intercept, the y-intercept, which is what we're calling v sub o. Now, if this, I'm just going to leave it like this, but if these were numbers, if the car's acceleration was 3 meters per second, that would be 3 meters per second times t, and then this is whatever your initial velocity is. So that's how you get your velocity function. All right. Case 3, if the velocity and acceleration are in opposite directions. Now I've talked about it like it's a separate case. Really, maybe I should just call it case 2.5, and I'll explain why here in a moment. All right. So when you get your graph, you ask yourself, at t equals 0, what is the velocity, right? And again, I'm assuming the velocity is to the right of a value v sub o. That would start this graph up here. Now, if the velocity were in the opposite direction, this point would be down here somewhere. It would be some negative number. But I'm going to continue on with my assumption that this car is moving to the right. However, here, the acceleration and the velocity are in opposite directions. So I think I'm going to go back and put that point a little higher on the graph. Just give me a little more room to work with. If the acceleration's in the opposite direction, right, in my picture, it's not this way anymore. Now the acceleration is this way. Whenever your velocity and acceleration are in opposite directions, that means the object's going to be slowing down. So a second later, we're going to be a little lower on the graph. Second later, a little lower on the graph. And again, assuming constant acceleration, it means that this graph will be linear. And we'll just stop it at a kind of an arbitrary time t. Now, writing the equations, it's pretty much exactly the same. Right? Your velocity is going to equal acceleration times time plus your initial velocity. And the only difference is if your acceleration is to the left, that, whatever is right there, is going to be a negative number. Over here, if your acceleration is to the right, that's going to be a positive number. So that's how you write these velocity functions for any given object here. Your velocity will be constant if there is no acceleration. Your velocity will be linear with a positive slope in situations like this, where we've defined right positive and then the velocities to the right. And when your acceleration's in the same direction, that's going to give you a positive slope like so. Acceleration in the opposite direction, that's going to give you a graph that looks like this. And functionally, the difference between these two, over on the left, your acceleration is negative. Over on the right, it's some, on the left, it is some positive number. Over on the right, some negative number. And again, the plus and minus signs are all dictated by the velocity and acceleration as they relate to your coordinate system. So I'll make another video about that. This is probably good enough for now for this video. I hope that this helps. Have a great day.